So A pk minus 1 tilde. But now I want to write this in terms of not pk minus 1 tilde, but just plain old pk minus 1. Actually, there's even more that I can do with this, because using a relationship between the residuals and the search directions, rk minus 1 is the same as pk minus 1 minus, well, where did I get that from? Oh, okay, it's just an unfortunate choice of notation. That should be, I have beta k in the notes for some reason, but it should just be uk. pk minus, actually that should be minus 1. Okay. Transpose A pk minus 1 tilde, but because the search directions are A orthogonal, this transpose, so pk minus 2 transpose A pk minus 1 tilde, that's going to be 0 anyway, so this term is gone. So in fact, it doesn't matter that I mislabeled it in the notes. It's 0 anyway. And I don't want this tilde in here, so I'm going to rewrite that in terms of the actual search direction. So wk minus 1, pk minus 1, transpose A pk minus 1 all over the norm of rk minus 1, 2 norm. Okay, so that takes care of that expression. And then the other relationship from the previous board, rk transpose rk, which is minus wk minus 1 rk transpose A p tilde k minus 1. Again, I want to get rid of the tilde, so that's minus wk minus 1 rk transpose A pk minus 1 all over 2 norm of rk. All right. Now, if I recall my expression for mu k that I had a little while ago, that is minus pk minus 1 transpose A rk over okay. Now, if I compare those inner products with what I have here, I have this one up here, and I also have this one. So this one is the same as what I have in the denominator here. This is actually the same as what I have in the numerator over there. Yes, the order is reversed, but A is a symmetric matrix, so it turns out to not matter. So what I can do is I can actually, let's see. Over this page more. All right. So I probably cleaned all the mistakes, but apparently I haven't. Dang it. Oh. Okay. I replaced this search direction, so that should be k minus 1. I have rk in the notes by mistake there. Okay. So now if I divide this expression by this, the norms will cancel, the wk minus 1s will cancel. So effectively what I'm going to have is minus RK transpose RK over RK minus 1 transpose RK minus 1. Okay. That's the problem dealing with, because the notes it says it might be supposed to be there, but everything on the board says that it should not be. And I'm going to have to try to resolve which one is actually correct. Okay. But yeah, I mean, I'm aware of a discrepancy. So, the thing is, when I went through these notes a long time ago, I found a bunch of mistakes and I thought I corrected them, but maybe some still through the cracks. So I'd have to look this up against the official cosmic gradient method. Okay. Now, so we'll hold that thought for now. Although actually, oh, I'm going to get a different, oh, no, okay. Now, because the thing is, as a result of this, there's no need for a matrix vector multiplication. That was needed in here, but now that's eliminated. So that helps make things more efficient. Okay, the last piece we need to make everything as practical as we need it to be is, if we go back to the solutions, how those are computed. We have xk is equal to xk minus 1 plus wk pk tilde. And we can get wk, the trouble is we need that LDLT factorization to get it, and we don't want to have to go through with that. So there's a simple relationship that we come up with. So first I'm going to write this as xk minus 1 plus nu k pk without the tilde. So nu k is some unknown constant, or maybe we don't have any simple formula for it yet, but we can try to find this by other means. But the thing is, we also have the same constant coming up in the relationship between the residuals. Rk plus 1 is equal to Rk minus nu k a pk. So if we can find a good way to compute this constant, then we're all set. And it turns out that that's actually easy to do because the residuals are orthogonal. So I can take the dot product of both sides of this with Rk and now I can solve this whole thing's equal to 0, for nu k. So nu k is equal to Rk transpose Rk over, oops, I forgot an Rk transpose here. Rk transpose a pk. All right. Now, it turns out that because of the orthogonality of the search directions, the A orthogonality, I can actually replace this with pk transpose a pk. And we can see from this inner product that it's guaranteed to be positive. It doesn't really matter which one we use, but at least this one is nice and symmetric. Okay, so now, finally, we can put the entire algorithm together, and then I think we'll be almost out of time. Mercifully so. You get to fix the book.
That just sounds awful.
Okay. So, the conjugate.
Dr. Lambers.
Yeah.
I'm sorry. Will you go? We're trying to. We can't tell it on this other board where you have the 0 equals all that stuff.
Okay.
What is the say new K, what is that last
Oh,
term?
new K.
No, above. Yeah, and go all the way over the new K.
Oh,
What does that say?
oh, I forgot an RK transpose in here.
Okay,
So I
so
mean,
new K, RK transpose A?
Yeah, A, PK. Yeah.
Okay, thank you.
Okay. Actually, I'm quickly looking up conjugate gradient method. A very description of the algorithm. I'm not sure how consistent it'll be with whatever description I have here, but if it can help me resolve the question of whether there's a dang minus or not. Okay. There's no minus. So, whew, okay. So, the source I used for all this was Demel. So I'll look at my bootleg copy of that and see why I had that in there. Okay, so conjugate gradient method for AX equals B, A is symmetric positive definite. So we start our iteration counter at 1. Our initial residual is just B. Our initial solution is just 0. That's our initial guess. Okay, so as long as we are not converged. Okay, now if we're on our first iteration, then we'll set our first search direction is equal to our residual. So we're just using a straight gradient in this case. Otherwise, I'll set mu k equal to RK transpose RK divided by RK minus 1 transpose RK minus 1. So after we have one full iteration under our belt. And then the search direction, the new search direction will be the gradient, RK, plus mu k times the previous search direction. Okay. So now the search direction for this current iteration is taken care of. And then for convenience, I'll carry out the only matrix vector multiplication that we need. BK is APK, so now I can use that further down. So new K is RK transpose RK over PK transpose BK. And then I can build my solution. So XK is XK minus 1 plus new K PK. And then I use the same constants to get my new residual. Okay. And then I'll just bump up my iteration count. And that's it. So I can, somewhere in here, put a test for convergence. Like, if this vector I'm adding on to my previous solution is too small, I can tell it to stop, for instance. I can also look at the residual, but this part would be likely more reliable. Okay, so that is the conjugate gradient method to solve a typically a large, sparse, symmetric, positive, definite system. Okay. Okay. Now, so one thing about the conjugate gradient method is it's actually guaranteed to converge within n iterations for A being an n by n matrix. So in that sense, it's technically not really an iterative method because you know when it's going to terminate. Now, round-off error might throw that off, but mathematically speaking, you only need to find a number of iterations because what will happen is your search directions will eventually occupy the whole vector space. They'll cover everything, so you can't help but get the solution. However, A is generally large when this is used. You don't want to take n iterations. You want to converge a whole lot faster than that. Now, since I have a little time, but I won't go into all the gory details because I think it's safe to say we've all suffered enough. Okay. The problem is if A is ill-conditioned, so norm of A times norm of A inverse is too large, this iteration will still converge very slowly. So we need to do something about that. Okay. So conjugate gradient method can be unbearably slow. Maybe not as bad as steep descent, but still bad. Conjugate gradient, I'll just abbreviate as CG from now on. Okay, so the workaround for this is known as preconditioning. Now, before I describe mathematically what preconditioning is about, the main idea behind it is to transform the original problem, ax equals b, into a new problem like a tilde x tilde equals b tilde, where the new matrix a tilde is approximately identity. As you said in your presentation this morning. So, because can't get any easier than that to solve the system. So we're going to try to get as close to identity as possible. Identity is perfectly conditioned. That's the main thing. Is we want a better conditioned matrix, so then we can apply a conjugate gradient to this system and get the fast convergence that we went through all this trouble to get in the first place. Okay, so what is the new system? So A tilde has this form. It's C inverse A C inverse. X tilde is C times X, and B tilde is C inverse times B, where, now what about C? What is this matrix C? So C is a matrix that has to be symmetric, positive, definite. Okay. Now, now the thing is, I won't go through all the details here because I'm running out of time, but the result of this is in the notes. That if you apply a conjugate gradient to this transformed system, we need the symmetric positive definite to make sure that the new system is also symmetric positive definite so that you can apply conjugate gradient to it at all. So if you replace all traces of the original problem with a transformed problem in the conjugate gradient algorithm, it turns out that by simplifying a whole lot of things, the only time a preconditioner is actually used is in this one step. You're solving a system, mzk is equal to rk, where rk is a residual from the CG algorithm, so that hasn't changed at all. Zk is a solution of the system, and what is m? M is equal to c squared. So matrix C never actually appears in the preconditioned conjugate gradient algorithm. Only M does. So M is referred to as the preconditioner. And there are different approaches. Coming up with preconditioners is a very active research area. Not just for conjugate gradient, but for other iterative methods that I'll talk about. because it's so important in order to set up your iterative method to be able to succeed and converge rapidly. So I'll give you one choice of for capital M that's frequently used. So an example of this, I can let capital M equal to H transpose, where H is the incomplete Cholesky factor of A. So what you can do is A has a Cholesky factorization because it's symmetric positive definite, but you can approximate this by H transpose, where, so what's the difference between Cholesky and incomplete Cholesky is this. Remember, A is sparse. So what you can do is you can act as if you're performing a Cholesky factorization of A, but if a certain entry of A is too small, you just ignore it and treat it as 0. So H would be like a sparser version of a true Cholesky factor. That way it's more efficient to use. And if you define M this way, you have this Cholesky factorization already. So solving this system is easy. You're not even doing any Gaussian elimination or Cholesky factorization. You're just doing forward and back substitution. So, so solving this, and it's very important, whatever preconditioner you use, this has to be easy to solve, or it defeats the whole purpose. Because the rest of a conjugate gradient algorithm is very efficient. There's a matrix vector multiplication, and everything else is trivial. So each iteration, you're only allowed to do order n squared work. Well, if this system here, so you need to be able to solve that order n squared operation. So if it's already pre-factored like this, then you have that. So that'll work. Okay, so that's the conjugate gradient method, derived very painfully from Lanchel. Sorry about that. I guess I don't do this very often in class. I've never done it in class, I don't think. Actually, no, I haven't. So, okay, so what I will do over coming weeks, the next couple weeks, is other iterative methods that are related to conjugate gradient and Lanchos, because this is only for symmetric positive definite. We want to be able to apply this to more general matrices. So I'll show you how we can do that. And hopefully we'll